Our second speaker for today is Harrow, talking about quantum expansion.
Okay, so today, what I'll tell you about today is not so much new work, but a review of a lot of things that have happened in quantum expanders, which are a somewhat widely useful technique, not quite as widely useful as classical expanders, but I think something that has potential to be an important basic tool in a lot of quantum information constructions. So I'll begin by just briefly reviewing classical expander graphs. And then, because the quantum expanders will be sort of a generalization of those in a particular sense. So an expander graph, for our purposes, will be an undirected graph. And the graph is called an expander because all of the sets are expanding. So what do I mean by that? The expansion, if S is a subset of vertices, then the expansion of a set is defined to be basically the fraction of edges that start in that set that end up outside of it. So the probability over all edges that one vertex is outside of the set, given that the other one is inside the set. So it's always a number that's between 0 and 1. It's 0 if the set is just disconnected from the rest of the graph, or if it's the entire graph, and it's 1 if all of the edges starting the set leave that set. And the expansion alpha is the minimum over subsets of no more than half the vertices of the expansion of that set. You have to pick some kind of threshold, like half the number of vertices, because if you take S to be the entire graph, then this number is trivially 0. And once you start to get to 99% of it, for example, then of course there'll be some set where no more than 1 in 100 of the edges is leaving. And so it's conventional to take this to be something like half the edges in the graph. Yeah?
Is there a factor depending on the size of S that's missing? Or is one of the endpoints in S in your probability?
This is a conditional probability. This is a conditioned probability of this happening conditionally on that happening. So there's no reference to the degree or the size of the graph or anything. Typically, I will consider deregular graphs with n vertices. I'll also consider undirected graphs. You can relax sort of the condition that they're regular and that they're undirected, but it won't really be useful for me to go into that here. Okay, so this is one definition. One definition of an expander graph is that if alpha is greater than some constant, then we say that the graph is an expander. And so right away you can see this doesn't really make sense if you just talk about one graph by itself, because what do you mean greater than a constant? What constant? So it's normal to talk about an expander, a family of expander graphs. So perhaps for a sequence of n, maybe for all n, or for a sequence of increasing values of n, perhaps d, the degree will be fixed, and alpha will be perhaps changing, but it'll always be greater than or equal to some constant even as you increase n arbitrarily. So here, constant would mean independent of n. And so technically what we're talking about is a family of expander graphs. But I'll do what most people do and just say an expander graph, leaving the family part implicit. Okay? So there's always some positive. For any connected graph, alpha will be positive. But it's non-trivial. Having it be always greater than or equal to a constant is not always trivial. For example, if you take a line or a grid or any finite dimensional graph, then alpha will shrink with n. Okay, so that's one way to describe them is in terms of this sort of combinatorial expansion parameter. An alternate definition is the spectral definition. So let A be the normalized adjacency matrix. So in quantum notation, you could write this as sum over all of the edges of this term. And so it's a matrix of the 1 over d in each position where there's an edge. And let's say that, so this adjacency matrix, the top eigenvalue will always be 1, corresponding to the vector of all 1s. And the second eigenvalue, let's say it's 1 minus epsilon, how much this is less than 1, so the value epsilon turns out to tell you how good of an expander it is. One way to see that is if you consider the random walk corresponding to this graph, where you start at a vertex and pick a random neighbor, then the probability distribution will be multiplied by this matrix A. And so it will eventually converge to the top eigenvalue, to the eigenvector corresponding to the top eigenvalue, the uniform distribution. And the rate at which it does it will be given by the gap between the second largest eigenvalue and the top eigenvalue. I'm sweeping under the rug issues if the graph is bipartite. Let me just ignore that issue for now. I guess if you want to be a little more precise, you could say that epsilon is the minimum of lambda 2, 1 minus lambda 2 of A, I guess 1 minus absolute value of lambda n of A. If the graph is bipartite, then the bottom eigenvalue will be minus 1. And then you will not converge. Then you could, if you do the random walk, you might just bounce back and forth between the two halves forever. You'll never converge to the stationary distribution. And so you'll also have to demand that this thing be bounded away from minus 1. But in many cases, you don't have to worry about this condition. And I'm going to be a little imprecise and just talk about lambda 2 here. And sort of implicit in all of that is really we also do have to worry about the bottom eigenvalue, but I'll never discuss a situation where it'll be an issue.
Well, the cleanest way to say it is that all non-principal eigenvalues in
That's right.
absolute value are less than 1 minus epsilon.
That's right. So the eigenvalues
Because
are in a range from minus 1 to 1. There's always an eigenvalue here. And then what you'd like is that they all live in this, you'd like them all to live in this interval here. So another way to say that is if you take the adjacency matrix and you subtract, what is the top eigenvalue? It's, let me call it U, where U is 1 over root n times the all ones vector, then this thing should have operator norm less than or equal to 1 minus epsilon. So you take the adjacency matrix, you remove the part corresponding to the top eigenvector, and what you're left with should have norm less than or equal to 1 minus epsilon. That's maybe a cleaner way of saying it. Okay, so this is an alternate characterization of expanders, and it's closely related to the combinatorial one by the bound I believe this bound. One way to see this is this minimum here is over subsets. And so basically one way to see it is that you can think of both of these as variational problems. So this is the minimum expansion over subsets, and this one is the maximum of, so lambda 2 is the maximum of VAV where we maximize over v that are orthogonal to the uniform distribution and that are unit vectors. So over a particular class of v. So both of them can be characterized variationally. And one particular class of v that we can take are ones. So what do the v's have to be? They have to be orthogonal to this vector u. So they cannot. That means if you add up all the entries of it, it has to add up to 0. So if they're real vectors, some of them have to be positive and some of them have to be negative. And one particular class of candidates for these things, cat v, would be things that look like some constant times the indicator function on some set minus some constant that's times the all one vector. So in other words, all the positive values are the same and all the negative values are the same. And you could, a restricted thing you could do is just maximize over these vectors v. Over this restricted class corresponding to be all the same positive value on one set and then all the same negative value on the rest of the entries. And it turns out if you do this restricted maximization, you get exactly something that exactly corresponds to this minimization. It corresponds basically to maximizing over subsets. And so that explains kind of the easy part of this bound. That basically this relation right here says that when you that this minimizing over sets corresponds to doing the eigenvalue calculation over a restricted set of vectors. What's a little more non-trivial is this bound right here. So to argue that, to go in the other direction, to say if all sets are expanding, then this also tells us something about the second largest eigenvalue. So another way to say that is if all of these, if you only know this quantity here for vectors that have this restricted form of being all the positive entries the same and all the negative entries the same, that nevertheless tells you something about general vectors. That's this second part, which is called Cheeger's inequality, and it's a slightly more complicated calculation. It's still not too bad, and you can kind of imagine why it should be true, right? If you can control this quantity for things where all the positive entries are the same and all the negative entries are the same, how different can it really be by letting your positive entries range over some have some be high and some be low? These quantities shouldn't be dramatically far apart, and that intuition is confirmed by the fact that you just lose a square root factor. Okay, so this is kind of the basics of classical expander graphs. A few other things I want to say about them. So one thing you can ask is, what are sort of the range of parameters that are possible? One thing that's often exciting about this is that alpha or epsilon are independent of n, and there's another parameter here which is d, and it turns out that the best these can be in terms of d is, let's see, so you should always have lambda 2 roughly greater than or equal to 2 root d minus 1 over d. This is more or less the optimal that's possible, and this can be achieved by what are called Ramanujan graphs. The reason they're named after Ramanujan is it's one of the less accurate pieces of scientific naming, I think. So I'll explain why they're named that in a second. It's what?
You want Selberg graphs?
Right. Yeah. That would be better, I guess. So So this is sort of the limit of what's possible, is that this thing scales. Basically, you can think of it as going like 1 over root d. And one way to understand this is we're multiplying by a factor of 1 over d for this walk. So it'll never be less than 1 over d. And the square root refers to this is basically the second largest eigenvalue of what is in a sense the best possible expander, which is the infinite deregular tree. So the point of an expander is everything is extremely well connected. You know, you go somewhere and you go somewhere else, and you're basically going to as many new places as possible. For whatever set you have, most of the edges lead out. When you take a random walk, you're very unlikely to return to where you came from. And the tree, the infinite tree, is in a sense the best possible expander because the only way to return to where you came from is to literally backtrack. You'll never encounter a loop. If you take this fork and then this fork and that fork, you'll always experience new places. The only way to return to your vertices is just walk back on the edges that you came from. And even on the infinite tree, if you take a random walk, there's some return probability. If you take k steps, then there's some probability exponentially small in k that you will return. And this corresponds to the second largest eigenvalue. And you can calculate that return probability pretty easily, and it turns out to be basically this quantity to the kth power. So that's why you'll never do better than that. Ramanujan graph saturate it. And this was achieved first by Lubatsky, Phillips, and Sarnak in, 87? 80-ish? 88-ish? And using math techniques that related to something that Ramanujan did, hence the name, it's also known that random graphs are almost Ramanujan. So they achieve basically slightly larger than this value. And it's possible, it's often interesting to have graphs that are not quite Ramanujan, but merely have constant, this is, for most applications, this is good enough. And there are a number of constructions of this. I guess the LPS one is one. There's one by Margulis, which involves just sort of a relatively simple group theoretic one. And I guess the two main techniques for constructing them. One technique is to use recursion. So basically to take a small graph and kind of build up bigger ones from that. And some of the techniques used here are the zigzag product, or more generally an idea called a lift. And I'm not really going to define either of these, but I just want to sort of give you pointers to the literature that these are kind of some of the ways of constructing them, basically in terms of building up bigger graphs from small ones, and these have become very, very effective. Another big method is to use a Cayley graph. So what a Cayley graph is you have a group G and a generating set gamma, and the vertices correspond to the group, and the edges correspond to all of the ways. So from a vertex, its neighbors are all of the ways you can multiply by an element of the generating set. So it's all of the pairs G times GH, where H belongs to the generating set and G belongs to the group. And to make it undirected, maybe we'll say that the generating set contains all of its inverses. So this is called a Cayley graph, and there are a number of expanders based on Cayley graphs. The LPS expander is one example, but since then there have been many, many more constructions for many other groups. Yeah?
So when using the Cayley graph, what's the hard part? Finding the group or finding the specific generators that do the job?
Probably more the generator. I mean, most of the groups are... Actually, it's more often it's finding the generator. In some cases, the groups can be kind of complicated. So the zigzag product, I think you can interpret as being the Cayley graph of a semi-direct product of groups. And I think that's the case where no one would have looked first at the groups and then figured it out, but they did it in this combinatorial way and then interpreted it as a Cayley graph. I think in many cases, the hard part is really just proving it. You can often come up with it. I'll mention one thing that was a big open question for a long time, which is to find a constant degree Cayley graph expander over the symmetric group. And that was a huge challenge. And I think there the challenge was to come up with a generating set as well as to prove it. Yeah.
Well, for the calligraphs, like one remark is that like there are group theoretical restrictions. Like for instance, it cannot be an abelian group, and I think there is a paper about that. That there
Right.
are certain, even maybe a solvable group is not good, but I forgot. But the other thing to be mentioned is that so there is this recent breakthrough of like Dan Spielman, like Nikhil
right.
Srivastava and Adam Marcus with beautiful construction. I mean based on multilinears.
Who are the authors? Spielman, Srivastava, and
Srivastava
and
Adam Marcus, I think.
Right. So what they have constructed is so one open question is: can you construct a Ramanujan graph for any n?
For any degree.
Any degree.
The exactly Ramanujan graphs only have p and p plus 1 degrees where their p are primes
Right.
or powers of primes.
Right.
But it's still unknown. I mean, they
Right.
answered that
They achieve it for bipartite.
There exists Ramanujan graph of all degrees, but it's still unknown how to find them.
But I think they did it only for bipartite, right?
Yeah, but, I mean, it still answers the question if they exist.
Yeah.
You know, for a given degree, can you find the Ramanujan graph? The answer is it exists, but we don't know what it is.
Right. But I guess what I mean is a bipartite expander is a slightly, a different object.
Right. So
Yeah. But the main question is still open.
It's still open.
That's
We
right,
don't
that's
know
right.
if-
Yeah, so right, so these LPS things are based on particular groups. The groups correspond to 2x2 matrices over FP, or over finite fields. And so the degree is sort of constrained by this thing, and only some degrees are possible and some values of n are possible. And what Marcus, Spielman, Srivastava do is attempt to resolve the question of can you construct a Ramanujan graph of any degree, and they solve this kind of related question of a bipartite expander, which I haven't defined, but it's pretty close. And it looks like they almost solve it for general expanders, but that's still a nice open question. Yeah.
Identify corresponding vertices from bipartite expander.
Why can't you identify vertices?
What do you mean identify?
Opposite vertices or something?
I'm sorry?
It's not unclear that you
But then you get different degrees, of course.
You would preserve expansion. Oh, I see. You get some
This is
expansion.
tight. This is for Ramanujan.
Ramanujan expanders. Yeah, you might lose half the expansion or something like that.
Another thing that's known is if you take a random with 2 lift, you get like a 10 with d plus 1 expander, but you don't do it.
Okay, good. So the last thing I'll say about this is applications. And there's a ridiculous number of applications. There are applications to codes, to de-randomization, to routing, to things involving geometry. I think the general rule is if your problem involves graphs, you should consider looking at expander graphs to see if it has potential use. And even if your problem doesn't involve graphs, but involves something like geometry or trying to prove the PCP theorem, you should probably also consider expander graphs. So they're really very widely useful. There's one other thing I want to say, which is what Mario said, that abelian groups do not work as Cayley graphs. And many sort of everyday graphs, like the grid and anything in a finite number of dimensions, for kind of a related reason, also doesn't work as an expander graph. So the geometry of these things is also pretty interesting. I guess James Lee has done a lot of work on showing them as sort of the geometry is sort of hyperbolic. But yeah, I will not get into that too much, but that's also a nice area for these things. Okay, so that was a lot on classical expanders. Let me talk about quantum expanders. One last thing about classical expanders, which is that we can write this adjacency matrix as in a different way as well. If the graph is deregular, we can write this as an average of d permutations. So these are our permutation matrices, and they correspond to for each vertex, you have the D edges coming out. Just assign each of these edges to one of D different permutations. One way to see this is if you take the expander graph and then construct a perfect matching on that graph. That perfect matching will correspond to a permutation. And then remove all of those edges, and you're left with something that's D minus 1 regular, and then repeat. Okay, so the quantum analog will kind of build on this. So this says that we have a collection of D permutations, and if you choose one of them at random, it mixes well. So a natural quantum analog is to say that you have D unitaries, and if you choose one of them at random, it'll mix well. So let's define a quantum operation to apply one of D different unitaries. And as with the classical case, we'll ask that this be Hermitian, meaning that this collection of unitaries contains its own inverses. So it might be that you apply one of D over 2 unitaries, or you apply one of their daggers, for example. You could talk about non-Hermitian quantum expanders, and it's sort of interesting that's something that we don't know, we don't understand super well, but there also aren't that many compelling applications of it that have led us to think about it that much. Okay, so again, we can talk about the spectral gap of this thing. So we can define 1 minus epsilon to be the second largest eigenvalue of this map. Because it's Hermitian, it's a map from matrices to matrices. We can think of it as a linear operator. We can talk about its eigenvalues. And just like the classical characterization, where we subtract the projection onto the uniform distribution, here the uniform distribution is like the maximally mixed state. And so the channel that maps you to the maximally mixed state is called the depolarizing channel. So the depolarizing channel takes any matrix X and replaces it with something proportional to the identity. So take the trace of X, divide by n. So this is an n-dimensional space, and give the identity. So if you put in any density matrix, for example, this will output the maximally mixed state. So you can take this operator, subtract the depolarizing channel, and then you've removed the top eigenvalue. And what you're left with, if you look at the 2-to-2 norm of this, so that means the maximum output Schatten 2 norm over all inputs with Schatten 2 norm equal to 1, then this gives you precisely the second largest eigenvalue. It's really just like what we're doing with matrices, right? This operator norm is just what is the largest output 2 norm given an input vector of 2 norm 1. We're doing the same thing here, except the outputs and inputs are now matrices instead of vectors.
What is X?
What is X? X is just what these things are acting on. You can think of it like a density matrix, or maybe the difference of two density matrices, or something like that.
Can you remind me what the Schatten norm?
Yeah, so this is equal to trace x dagger x all square rooted. Another way to say it is that if you turn x into a vector, it's just the 2 norm of that vector. Another way to say it is that if you look at the eigenvalues of x, it's the 2 norm of, for a Hermitian matrix, that's the case.
So it sounds like the Frobenius.
It's also for.
It's also the Frobenius norm. It's also the Frobenius norm. Yeah.
Are you going to care about the action on non-Hermitian X at all, or because the definition might be slightly different?
No, I don't think we'll need to use non-Hermitian X. Yeah, I guess this last one, it should be like singular values or something.
I mean, also just the value of the eigenvalue might be different depending on what space you're making.
Maybe. Maybe, I think not, but I'm not sure. Okay, so this is a little bit awkward to think about superoperators. You know, it's nicer to think about things just like matrices. And in general, the map where you take x to a x b, this we can think of that as, so this is a superoperator, right? An operator that acts on operator. So it takes a matrix x to another matrix axb. But we can just write this out as a giant matrix. And if we do, this corresponds to the operator A tensor B transpose. And according to that correspondence, this map E corresponds to 1 over D, sum over I, ui tensor ui star. So this right multiplication by ui dagger becomes just tensor ui star. And so this is basically under the map where you replace x with vec x. So another way of saying this is that A tensor B transpose applied to vec x is equal to vec of A x B.
Sorry,
That's sort of a more concrete way of doing that isomorphism.
sorry, I missed what you said. So what's this? You're
So-
doing some replacement of.
Right, so instead of viewing x as an n by n matrix, I want to view it as an n squared dimensional vector. And in that case, what acts on it will simply be a big matrix.
So is x positive or it does not matter?
It doesn't matter. In general, yeah, it doesn't matter. So
if it does not matter, then we can view it as a vector.
yeah,
Otherwise, we couldn't view it as a vector.
you still could. It's just the positivity would be a weirder
But
condition.
then it would be an extra weird condition.
Yeah. So
Sorry, your notation star is
conjugate. So dagger is conjugate transpose, and star is just conjugate. So if you do dagger and then transpose, you get a star. So, okay, so let's see how everything translates into this picture. If you take the right, so this is what the expander becomes. What about the identity and what about the depolarizing channel? So the identity matrix, well, that doesn't work. So the identity matrix under this map, the vector version of it looks like the maximally entangled state, right? So you could write this as root n times phi n, where phi n is just the usual maximally entangled state on two n-dimensional systems. So what does the depolarizing channel look like? It basically looks like the projector onto this state. So it looks like it gets mapped to this. So why is that? Well, what the depolarizing channel does is it takes the trace of x, which you can think of as the inner product of x with the identity. And so whatever you put in, it takes its inner product with the identity, and then it spits out something that's like the identity. And then the 1 over n is what you need to give the right normalization. Why is that? Well, the depolarizing channel, if you put in something proportional to the identity, you should get back what you put out. It shouldn't blow it up or shrink it. And same thing here, if you put in something proportional to the maximally entangled state, you should just get out exactly what you put in, not times any kind of scale. So this is what the depolarizing channel maps to. So this gives an alternate characterization of the expander condition. It says that 1 minus epsilon is equal to the norm of the difference between this operator and I'm just going to use this as shorthand for the projector, and this projector onto the maximally entangled state, where this is now the infinity norm, the Schatten infinity norm, or the largest eigenvalue of this thing as a matrix. Okay? So this is so far just at the level of definitions, but from this you get a very nice application to the task of bipartite measurement simulation. So
I got confused.
Yeah.
I thought that you're just using the regular way to view matrices
as vectors. That's right.
But here you're using something like Tchermakovsky representation.
I think you should write phi n tensor phi n instead of just phi n.
Here?
No, in the bottom.
Here?
Yeah, because it should be an n squared phi n squared matrix.
Yeah, I guess, there's this convention where if you just write psi, it stands for the projection onto psi. And I'm just using that convention. It's sort of, it saves you a lot of writing in the end.
Maximizes confusion.
But it also leads to confusion. But I didn't invent it. It's kind of, a lot of people use it. And I think it's good once you adopt it. Other questions, critiques? Okay, so one other way. There's one other way to interpret it, which is look at expanders. What is going to be the fixed point of this map, right? If you put in something and you multiply it by conjugate it by a bunch of unitaries, what is going to stay the same? Well, for sure the identity will. The maximally mixed state, if you multiply it by a bunch of unitaries, will stay the same. And what it means to be an expander is that nothing else does. So your difference from maximally mixed will get shrunk by an expander. That's kind of the definition of it. And in this picture, we see something pretty similar. So what is the unique state that is invariant? So suppose we have this. That's true for all. This is true for all unitaries U. What can you say about the state psi? Well, then you can say it must be the maximally mixed. The maximally entangled state. This is the unique. So if this is true for all U, that implies that psi is equal to the maximally entangled state. This is sort of the unique solution of that equation. Just like the identity is the unique thing that's going to be invariant under multiplying by all unitaries. And this measures sort of how good a job these UIs are of coming close to that ideal that you would get from averaging over all unitaries. So if I were to replace this with the average over all unitaries, I would get exactly the projection onto this. But instead, if I just average over some maybe very short list, I get an okay approximation to it, where the approximation is okay in operator norm. Yeah?
So I don't yet see an advantage to viewing it as a vector. So can you help me understand why we went down that route?
Like, what's the point of this equation?
No, what's the point of taking the density matrix and flattening it out as a vector? So far I didn't see any advantage to that. So.
Well, I guess, right. So what did we do? What did it achieve to flatten it out? We went from this equation to this equation.
And so why is that a step forward?
Great. So let's consider the following problem, which is you have Alice and Bob, and they share some state psi, and they want to make some measurement on it. And they want to measure, suppose you want to measure, you want to do a 2-outcome measurement. And your POVM outcomes are the projector onto the maximally entangled state and identity minus that projector. So another way of saying it is you have a state and you want to know, is this the max, are we sharing the maximally entangled state or something orthogonal to it? So you could do a Bell test, for example, and that would give you some kind of statistics about it. But suppose you really want to just perform this 2-outcome measurement as accurately as you can, because Bell tests have some kind of, you have to do many of them to gather statistics. What is really the best you can do? So one thing you can do if you have a small amount of quantum communication is you can use expanders. And the idea is, suppose that they really have this state. And, well, yeah, maybe I'll write down the circuit first. And I want to write it with time going from right to left. I hope that's okay. I think it'll make the equations nicer in a second. So here's how it works. They share some state psi, and they want to know, is this the maximally entangled state or something orthogonal to it? And Alice begins with a copy of this state. And then she uses it to do a controlled u sub I here on her copy of the big state. So this is a small d-dimensional register. This is a big n-dimensional register. Then, this continues, she sends her copy to Bob. So using a small amount of quantum communication, she sends this register to Bob. And then he does a controlled u sub I star. So what's going to happen? If this indeed were a maximally entangled state, then it would be invariant under all of the u tensor u stars. So all of these things would do nothing, and their state would stay the same as before. And intuitively, if these unitaries scramble it up really well, and this is orthogonal to a maximally entangled state, then each unitary should sort of take it to some new orthogonal direction. And so this thing will become entangled with the post-rotated state here. And so that is something you should be able to detect by looking at this register. And so what Bob will do is he will project onto the original superposition. So he'll do this projection and kind of output yes if it succeeds and output no if it doesn't. Okay? So let's look at the resulting measurement operator. So you have Bob's projection looks like this. And then identity for the two systems. Then you have these controlled unitaries. Uj tensor Uj star. And then you have Alice's preparation. Again with identities. And when you put it together, you just get 1 over d sum of ui tensor ui star. This is exactly the measurement that they have implemented with this protocol. And when I say the measurement, I mean this is the yes outcome. And then the no outcome is I minus m. Okay, so they want to do this, and instead, what they do is m I minus m. So they approximate the true measurement with this protocol. And now the only question is, how good an approximation is this? And the answer is, well, how? And so this means how different is m from the operator they really wanted, which is the projection onto the maximally entangled state. And so finally, that's the answer to Umesh's question of, what's the point of this alternate way of looking at it? It's exactly this equation, right? This tells us exactly how far this protocol is from what we would like it to be. Yeah.
So this is just, I think this can be translated to exactly what Mario showed in his talk, right? It's a Hamiltonian. I think it can be translated to Hamiltonian, whose spectral gap is something related to epsilon, and whose ground state is highly entangled, but the communication is local. It looks to me like it's the same thing, or it can be translated.
Oh yeah, that's a good point. Because because the communication channel could be there could be some Hamiltonian mediating that,
right.
And then the controlled unitary, right? So there's sort of the unique thing that satisfies it. Oh yeah.
Is the highly entangled state, or is the state, is the maximally entangled state?
What is the size of the channel that
So the size
just
of the
log
channel is log D, right?
Okay, right. So let's.
So just
Yeah.
just a follow-up question. Could you have expanders which have sort of, so if you just look at the expanders on both sides, could they have local structure?
Local, like
Some
in terms of
sense.
2-qubit gates.
Yes.
So you want to ask, can you do it efficiently?
I'm sorry?
You mean like, can you do it with an efficient circuit?
No, efficient circuit, I
Yeah.
Yeah, with set around
yes.
UIs.
You what?
With set around UIs, you'd be doing good too.
Well, what do you mean by local structure?
So, okay, really the ultimate thing would be to if you could use this thing as an attempt to trying to build a counterexample to area laws
Yeah.
in small dimension, then the question is, could you have quantum expanders on both sides which have a local structure, meaning that the circuit itself is local?
Yeah, you don't expect expanders from local,
Sorry?
fixed dimension.
Well,
Okay, maybe we should.
no, it's a very good question. I think, yeah, to get from this to a 2D area law counterexample,
Not 2D, but maybe higher D.
no, it's a good question. I guess yeah, so it'd be good to even precisely formulate what the condition on the expander would be. So let me just talk about this protocol. So the communication is log d qubits, and the error is lambda 2, right? This is the difference between these two things. If it were a Ramanujan expander, I realize that's a classical, we said for classical, then we would have that this would go like 1 over root d. So in other words, the communication would be like log of 1 over the error. I guess, twice log 1 of the error. If you had a quantum Ramanujan expander, and I'm a little over time, so I'll just say that quantum Ramanujan expanders exist. And so this is a, so this type of communication is achievable. And so this is an interesting thing in terms of communication complexity. One thing we'd like to know is there a quantum Newman's theorem? If you have a communication complexity protocol that uses a ton of entanglement, can you replace that entanglement with some fake entanglement that fools it? And the protocol, if the protocol only uses like a really small amount of communication, maybe it won't be able to tell the difference between a billion EPR pairs and some other billion qubit state with much less entanglement.
Sorry, what's the classical Newman's theorem?
The classical Newman's theorem says if you have a communication protocol that uses a ton of randomness, but very little communication, actually forget the amount of communication, but has a small number of inputs. So if the input size is n, but the amount of randomness is much, much more than that, you can replace all the randomness just with log n, roughly random bits, and the protocol will do almost as well. So can something similar work quantumly if you have some protocol that uses tons of entanglement, but say only very little communication? Can you get rid of the extra entanglement? So Rahul has an example of a protocol where something that sort of refutes that, and this can be viewed as another refutation of this, because this is a protocol that it uses a very small amount of communication, but can test an unboundedly large entangled state. And so the size of the entangled state has nothing to do with the amount of communication needed to test it. Right, so that's one implication. So now,
so this doesn't say anything about the function problem.
No. And so it's worth pointing out that Yaoyan has a very nice result of, so what do we know about reducing the amount of communication, reducing the amount of entanglement in communication complexity? I think Yaoyan's result is the only thing we know, pretty much, which is if you have something that uses q qubits of communication and an unbounded amount of entanglement, you can replace it with something that uses no entanglement and 2 to the q classical communication. So at least if the amount of communication is constant, then at least for communication complexity purposes, entanglement cannot help an unbounded amount. And so when you put all this together, what this says is if you want to get rid of entanglement in communication complexity, you cannot do it in sort of a black box way where you just replace the entangled state with some fake entangled state. But you really have to kind of look at the details of what the gates are and what the protocol is. Okay, so that's a bit of an aside. This is, I think, one application of expanders. You heard a very nice one from Mario yesterday, but it's possible that you've heard the same application twice if we look at it more carefully. Another application is in Matt Hastings' original paper that introduced expanders, where he uses it to construct a spin chain, a state with constant correlation length so a state in 1D, so like a spin chain in 1D, the correlation length is constant. The entanglement is linear in the number of qubits if you cut it, and it's the ground state of a gapped Hamiltonian, albeit one with where the terms act on many qubits, sort of logarithmic in the number of qubits. So if the total number of qubits, if it's n qubits, then it's log n local. So this is Hastings 07 was sort of the original motivation for quantum expanders. One of the original motivations for quantum expanders. And it's a little bit similar. So the tons of entanglement corresponds to the very large dimension of expanders. And the short correlation length corresponds to the large gap of the expanders in his construction. And I think I don't have time to really explain it, but just to say, if you build a matrix product state where the matrices involved are expanders, then this is the route to doing this construction. And there are some similar features in that there's a kind of very large entanglement and yeah, well, maybe I won't explore the similar features too much. Okay, so all of this would be worthless if these quantum expanders didn't exist. But it turns out a lot of the ideas from classical expanders go through to the quantum case. So if you pick a random graph will be an almost Ramanujan classical expander, and Matt Hastings showed that a random set of unitaries will be an almost Ramanujan quantum expander. And that proof is actually much, much easier because basically classical random objects or sort of random combinatorial objects are much more likely to collide and have bad things happen than random vectors. So if you take two random points, if you choose two random elements of an two random elements of an n-element set, the probability of collision is 1 over n. But if I choose two random n-dimensional vectors, they're almost certainly going to be nearly orthogonal, and the probability of deviating from that is exponentially small in n. So they're just things work out better in a sense in terms of random objects. There are also explicit ones. You can basically do all these things efficiently. We don't know everything quite as well, so we don't know how to get a efficient Ramanujan expander, but we know how to get one where the degree is sort of the square of what it should be for a Ramanujan expander, how to do that efficiently.
By efficient, you mean that the UIs are computational?
Right, so what we would like is that the parameters be as good as possible, and also if you build these things out of qubits, then you can do it polynomial in the number of qubits. And we can do it with slightly worse parameters. Using similar ideas, there's sort of a quantum zigzag product, and there's you can do it based on Cayley graphs and using representations. So
What's this paper? Where is this?
there's a few different papers. So there's one that, so there's one just by me in 2007 that does it for Cayley graphs. There's one by David Gross and Jens Eisert and somebody else that does it for using a quantum version of the Margulis expander. There's one by Tashma and somebody else, Benaroya, Avi Benaroya, that do the zigzag product. There's one, the original one by Hastings has a construction that is you use a classical tensor product expander and you add a phase. and then there's one, yeah, that's most of them, I think. By now there's quite a few constructions. So anyway, so these constructions exist, and you can do it efficiently, and for things like Mario's application, where you want it to be a small number of gates, it's actually quite important.
So
Yeah.
You said that there's an advantage in the quantum case because of lack of collisions.
To prove that random ones work, it's easier.
Okay. Are there other advantages because of this? Or?
You mean, well, it just achieves something totally different. I just meant an advantage in terms of it's easier to construct them. They're kind of incomparable. You know, it's not like if you have a quantum expander that will give you a classical expander or vice versa. They're similar, but not directly comparable. So, okay, I should wrap up. Let me mention two other. Yeah.
So, if you're looking for a quantum expander, is it like the same as looking for unitary designs, like one design?
Right. Okay. So.
Approximating the integral by some discrete sum.
That's right. So the difference between a design and an expander is usually in the norm that you have here. So if you replace this infinity norm with a 1 norm, then that would be what you would need for a design. And as a result, a design you cannot do with a constant number of gates. The number of gates has to, a constant number of unitaries. The number has to grow with dimension. However, so a design is strictly stronger than an expander, and you can get it, because of replacing infinity with 1, you can get it just by losing a dimension factor. And so some of our methods for constructing designs are based on basically taking an expander, powering it many times, and then just accepting that dimension loss. Yeah?
So, you mentioned expansion comes up in the context of the classical PCB Aram.
Yeah.
So is there a quick summary of your thoughts about where, what we can say in the context of quantum PCB?
I don't know how to make any connection there. It comes up in the classical PCP because you're applying it to the bits. You want an expander on the bits, and you want to replicate their information all over the case. I don't know how to do something how to even sort of make a statement that parses properly here. Let me tell you the closest I know how to come to that, which is you can think of this, so expanders are used in PCP via codes. So, and just that's much simpler than the PCP is the way expanders are used to construct error-correcting codes. So maybe quantum expanders can be used to construct quantum error-correcting codes. This is, in a sense, kind of like that. You can think of this as an error-correcting code that encodes 0 qubits. But you just want to know, are you in this protected space or are you far from it? It's sort of like detecting if there's an error for example, if you have a maximally entangled state and you want to know if some error has happened to it, this is a way of at least efficiently detecting it. And so one thing I would like to figure out is, can you use an expander to construct an approximate quantum error correcting code? We know that approximate quantum error correcting codes exist with dramatically better parameters than exact quantum error correcting codes. I think it would be cool if expanders had some connection there. But I don't know how to make that more precise. But that's sort of the most concrete thing in that direction that I'm able to say. Another question?
I'll ask later.
So, right. So one body of work has been, trying to construct these things. I've told you about a few sort of diverse applications of them. Another thing you can do is you can say, suppose you want to consider. So expanders say that if you apply it to a state, then the average of that will go to what it should do. But what if you want to control the higher moments of what happens? Then this is equivalent to taking this thing and putting a tensor k here. And then here, you have to replace it with something else, which I'm not going to write down. But that something else is what you would get if you average this over the Harrow measure. So it's no longer a one-dimensional projector, but it's some other beast. What you get then is something called a tensor product expander. and because it's an expander where the tensor products are controlled. And this is useful for controlling, as I said, higher moments, which can give you, if you want to get, for example, a stronger concentration bound, these can be useful. So if you want to prove that the output of a random circuit of depth d cannot be distinguished from from a totally random unitary by any distinguishing circuit of depth less than the 6th root of d, that's how you would do this, because by controlling the higher moments, you can show that any deviation of the output of this random circuit, of this pseudo-random circuit from what you'd get from the average, must get suppressed by an amount that relates to how many higher moments you can control. So I really don't have time to get into this, but this is sort of, if you want to ask where have things gone since expanders were introduced several years ago, one direction is tensor product expanders of controlling higher moments. Another question is, maybe your application doesn't call for moments, but it calls for some more specific things. So maybe you want to build an error-correcting code, or you want to do decoupling. And so there's been a lot of work by Brown and Fawzi, and also by Berta, Fawzi, Schultz, and Scher, on showing that if you have random circuits, okay, so there's a paper of me, Fernando, and Michał Horodecki that shows that random circuits give you tensor product expanders. But this work by Brown and Fawzi and collaborators shows that in some cases expanders give you more than you need. So expanders kind of control, these operators say whatever you feed in, this will do the right thing. Tensor product expanders are the same thing. You control all of the higher order moments. And I think this has sort of been a good starting point, but then for some applications, you might say, well, I don't need to control all of the higher moments. For my application, I just need to compute this. Maybe it is a degree k quantity, but it's a more specific quantity, and I can do something more refined there. And so this work by Brown and Fawzi has been a very nice recent example in that direction, where instead of controlling all the higher moments, you just make some kind of specific statement about it. And kind of the general area that this is the area of pseudo-randomness, of trying to say, instead of having a hard uniform unitary, can I simulate it with some much smaller amount of randomness? And expanders are kind of a nice, very general tool for it. Tensor product expanders are another nice general tool, but I think going forward we'll start to see kind of more specialized ones adapted to the particular application in mind. Okay, so thanks for your patience. I'll stop here.
So you talked about quantum Ramanujan expanders. But classically, you said that Ramanujan expanders are very natural because of the infinite tree.
Yeah.
And so that's what sets that's whatever 2 times square root d minus 1 divided by d. But so in quantum, there is no infinite tree, so what would be the analog of that? So what sets the bound for?
There sort of is. So
the ultimate bound. So
suppose you take e to the mth power of x. So this corresponds to applying a bunch of n times sampling a random unitary and applying it. And I said that this collection of unitaries contains its own inverses. So there's always a chance that you apply a unitary and then you apply that unitary's inverse and you come back to where you are. Or you apply u1 and then u2 and then u2 dagger and then u1 dagger and you come back to where you are. So there is again a notion of a return probability, and it arises in exactly the same way.
Mm-hmm. And then you do some computation and you get this ultimate limit for what you can get for.
It's the same calculation. It's the same return probability. It's the same calculation. It's kind of like, you apply a bunch of unitaries, and it could be that it's trivially equal to the identity because things just canceled, or it could be that it depends on the particular unitaries you use, and maybe it's close to identity, maybe it's not. And in the most optimistic case, you say, if it's not trivially equal to the identity, then it's as scrambling as possible. And that will give you the Ramanujan bound for the quantum case as well.
And so maybe a related question is that, well, in the Alon-Milman or whatever Chigger bound, you connected this eigenvalue gap with something combinatorial, so this conductance. So is there any notion or any analog of that? So we have seen the eigenvalue gap, but is there any?
Yeah, it's a good question.
Notion?
So
we have one with Frank. It looks essentially the same.
You just replace this with like a projector, I guess, or projector minus identity. Yeah. Oh, that's good to know. Is that published?
Yeah, it's in this chi-squared paper from.
Okay.
But it's hidden.
Okay.
Yeah.
Yeah.
So let's come back to your definition of the this spectral gap and
Yeah.
energy. So it seems to me it's more natural to use the diamond norm instead of the 2-to-2 norm.
Good.
And it seems in principle it's possible that you could have a quantum expander in that sense, but not in this sense, right?
Good. So the diamond norm is what we usually call those designs.
Okay.
And it's just for a different set of applications.
All right.
And one difference is that constant D becomes impossible. You have to have D growing with n if you want a good diamond norm approximation. And why is that? Well, if you just put in a pure state, then you apply a collection of D different unitaries, and you're in dimension n, how are you going to look close to the maximally mixed state? Even if you knew what the input was, and you had to choose the unitaries accordingly, you're not going to be close to the maximum mixed state unless D is at least n times 1 minus epsilon.
I guess that's when you restrict your operation to be the form of U mixture of U dagger.
Yeah, okay, so that's one nice thing you could do is you could relax it, just say let them be any Krauss operators. But nevertheless, the rank of the resulting output density matrix would be at most D. And so again, you would have that bound. So this is I don't want to say that's not important. Designs are very useful. Oftentimes we actually care about designs. One thing I didn't talk about is our K designs. And right now the only way we know how to show the existence of K designs is via K tensor product expanders. So we know how to construct a K tensor product expander and then you repeat it many times, amplify it, and then when you go to designs, you just lose a dimension factor. But it's possible that, as Brown and Fawzi did for 2 designs, that we'll be able to kind of get a more direct argument for K designs that will make it more efficient. But in general, the answer is yes, these are valuable things. They're related, but they're kind of off by a dimension factor. And so a lot of what we want to do for expanders is get something that's sort of constant degree. It's completely impossible for designs. And for expanders, it can be valuable for things like what Mario talked about yesterday.
So one way to characterize designs is to say that they look completely random against, so a K design is some set of unitaries that looks like par random against all degree K polynomial functions on the unitary group for a suitable definition of polynomial functions.
That's right, an exact.
Is there a way that you can phrase the expansion condition in terms of looking completely random against some particular well-defined class of functions?
So if you have a perfect design or a perfect expander, like, epsilon is equal to I guess in this case 1, or lambda2 is to 0. Those are the same thing.
Right, but so is there a way to phrase it? Let's say that so like Ramanujan expanders would be like analogous to a design. So you could define some class of functions so that they look perfect, but it's not all functions.
No, yes, it's not. It doesn't. I don't think so, but I'm not sure. So you can describe this in terms of indistinguishability. Design is something where whatever the input is, the output is indistinguishable. There's another way of, one way of thinking about expanders is that you're kind of adding randomness to the system as efficiently as possible. So another thing they relate to is extractors, where maybe you have some state which is pretty random, but you want to make it really look, say because there's an adversary, you want to make it look totally random. And so you want to basically add entropy to it. And expanders, Ramanujan expander is the most efficient kind of general purpose way of doing this. If you didn't know anything about the state and you just want to increase its Raney-2 entropy, an expander would be the best way to do this. But you still only increase it at the rate that you put in randomness. And so if you start from a pure state and you just add a little bit of randomness to it, you'll have very efficiently added randomness, but you won't have gotten all the way to the end. And so design kind of measures how well do you get all the way to the end. Whatever you put in, it just makes it completely random. Whereas for an expander, That's kind of not the goal. The goal is to like take some steps towards it, but deliberately don't make D too big, and so as a result, you're not fully randomizing. You're just kind of increasing the amount of randomness.
Okay, let's thank Aram again.